Yes, good day to all. And in this section, we are going to discuss about the sensors and actuators. Right. So, what is actually already a sensor, an actuator? Already we have seen some basics. Of course, we will discuss them in detail. And an embedded system is a constant interaction with the real world, and the controlling or monitoring functions executed by the embedded system is achieved in accordance with the changes happening in the real world. Right. The sentence is a bit complex, but the meaning is, when some changes are happening in the real world, the embedded system will sense the change and it will react accordingly. That is actually the meaning, we can say. Right. The change in the environment or the variables are detected by the sensors connected to the input port of an embedded system. And if the embedded system is designed for any controlling purpose, then the output of that particular controller will be given to the final control element or to an actuator, and that brings the controlled value into a desired value. It is achieved through an actuator connected to the output port of the embedded system, right? Again, I think you should have studied in your control system a normal closed loop system, right? The same thing, right? The control system in your second year you might have studied, right? So there will be a process variable, and that process variable will be sensed by the sensor given to the comparator. So E equal to R minus B, where R is the reference value, B is the feedback value, an error is compared, and this error is given to the controller. The controller will give the output of that, and that value is actually the manipulated variable which is given to the final control element in order to control, right? I hope you can just recall the closed loop control system which you have studied in your control systems paper, right? The same thing, of course, here will be applicable. Right, and this is actually a simple example of how that sensors and actuators, so that you can get an idea, better idea about this. So on the left hand side you can see there is a sensor. The sensor may be to measure any parameter. It can be a temperature, it can be pressure, it can be level, flow, pH, whatever it is, any measurable parameter that will be measured by a sensor. So in this example we are going to have a soil moisture sensor. So it's a sensor which is used to measure the moisture level, right, which is used to measure the moisture level in the soil. And then this value, of course, will be transmitted through wired or wireless transmission, and this data is given to the control center, right? And the control center, it will check whether the moisture level is sufficient or the moisture level is very high or very low. If the moisture level is very low, then I have to switch on the motor so that the water will flow, the moisture level will increase. If the moisture level is very high, then I have to switch off the motor, assuming that my motor is already running and I have to switch off it. So my final actuator is going to be the water pump or the motor, right? So in this diagram, actually what happens, so on the left hand side, the soil moisture sensor detects the unwanted water content. So that shows already you have enough water in there. So the sensor is actually a transducer which converts one form of energy into another form of energy, right? Most probably a non-electrical energy, non-electrical domain into an electrical domain energy, right? So that is the function of a transducer or a sensor, you can say. So the examples are temperature sensor, right? So the input is going to be a temperature, which is actually a non-electrical quantity. The output will be a electrical quantity, maybe a variation in the resistance, or it can be a voltage, right? So a non-electrical quantity most probably will be converted to electrical quantity, right? And that's actually regarding the sensor. And an actuator is the form of transducer device which converts in the opposite direction signals to the corresponding physical action. So here actually what happens, an electrical energy will be converted to a mechanical energy, something like, right? So the actuator is an output device which converts the electrical energy into a mechanical energy or movement in a stepper motor, right? That is one physical action or an example here, right? And in between these two things we need an optocoupler. What is actually an optocoupler, right? Normally what happens, the output of the process will be actually a very high voltage will be there, or very high power will be there, and the microcontroller will be using with very minimum power, all right? And normally what happens, the output of the microcontroller will be used to control a motor. The microcontroller will work with 500 milliamps or 1 amps. The motor or pump will be working with 15 amps or 20 amps. So these two things to be interfaced. So we need some sort of drivers in between. right? Even if all those things are there, if there is a reverse current, then your microcontroller, or in general the controller, may get affected by this high voltage or high current. In order to avoid that, we are going to insert some sort of optocouplers. So this optocoupler provides a physical separation between the I/O interfaces, right? I think you can see that on the left hand side you can have a LED, on the right hand side you can have a phototransistor. So if I give some input from the left hand side, right, so the LED will be glowing, and this LED glow will be sensed by the phototransistor, so my output will also be a 1. Suppose if I give the 0 value, the LED will not glow, so phototransistor will not sense any output, so my output will be 0. So the mere passage of data from left hand to right hand side, if you pass through a normal wire, there will be a physical connection between the left hand side and the right hand sides, right? But if you use an optocoupler, there is a physical separation, but they are connected through an LED and a phototransistor. The data will be transmitted, but not physically inside an optocoupler. So that is actually the function of an optocoupler. It's a solid state device to isolate two parts of a circuit, and it contains an LED and a phototransistor in a single housing. And the following figure, of course the figure shown indicates what is an optocoupler, right? And it's in electronic circuits, an optocoupler is used for suppressing the interference in data communication, circuit isolation, high voltage separation, and simultaneous separation, signal intensification, etc. Right, so they are mainly useful for data communication, circuit isolation. That is what I said. There will not be any physical wire, right? So there is actually a break in between this. A high voltage separation, one end will be high voltage end, the other end will be low voltage end. So I have to separate using this optocoupler. Something like that will be there. And it can be either used in input circuit as well as the output circuit. Wherever I need to protect, I have to protect through this optocouplers. And it is available in the form of ICs from different semiconductor manufacturers, right? So there are so many companies are manufacturing, and one Fairchild Semiconductor, that's actually the company name, they manufacture an optocoupler IC. They name it as MCT2M, right? And this particular image illustrates the usage of optocoupler in a circuit of the input and the output device, with the microcontroller as the system core, right? On the left hand side you can see there is an input device is available, and if the input is 1, then this LED will be glowing and the data will be communicated to the middle portion, right? So the middle portion is actually the 89C1, which is actually a microcontroller. Suppose if there is a sudden surge of voltage in the input side, there is a short circuit, then what will happen? That high current will be coming there, and that high current will burn the left hand side LED. So the high current or high voltage will not affect the 89C51. So that the 89C51 is protected from high current or surges, right? That is actually the protection of the left hand side. In a similar way, on the right hand side again you can see there is an LED is connected here, and the other end of the LED is connected to the port pin of the microcontroller. And suppose if the port pin is 0, then what will happen? The microcontroller, I mean this is an inverted logic, right? So if the port pin is 0, the LED will glow and the output will be 1 in that case, right? I will be getting output 1. If the input pin is 1, the LED will not glow, the output will be 0, right? So the output inverted will be getting at the output. So I am going to protect my 89C51, which is actually a microcontroller, by two optocouplers, one in the input side and one in the output side. So I can I can protect my microcontroller, right? And now we are going to discuss about different communication interfaces. And in the communication interfaces, again we have seen wired and wireless communications. In the wired communication, like I2C, SPI, UART, serial and parallel communications are available. And external communication, something like wireless, right? Like infrared, Bluetooth, wireless LAN, which is actually Wi-Fi, radio frequency waves, RF communication, GPRS, and everything are also different types of communications are available, of course, right? And onboard communication. So an embedded system is a combination of different types of components arranged on a printed circuit board, right? So it will be having a microcontroller, it will be having some memory, some timer will be there, a crystal oscillator will be there, maybe, right? Supposing if the oscillator is not inside the processor, right? Sometimes it may be inside the processor itself, right? So in those cases, a board will be containing different chips that is arranged on a printed circuit board. And this onboard communication interface refers to the different communication channels or buses for interconnecting the various integrated circuits and other peripherals within the embedded system, right? And serial interfaces like I2C, SPI, UART or one wire or parallel bus. So these are all some of the communications that are available, the onboard communication, so that the data can be brought in or brought out from this board. And the inter-integrated circuit, that is called I2C, right, or I2C, whatever we can call it as I2C, is a synchronous bidirectional half duplex two-wire serial interface bus. So what is actually the meaning of this? Bus means it's a connecting wire, we can say connecting wire, right, which can carry the data. And serial interface means there is only one wire, so the data will be sent one bit by one bit, either from MSB to LSB or LSB to MSB, depending upon the standard, right, serial bus. And two wires, there may be two wires will be available, and it is half duplex. So simplex means only one-way transaction, the other way transaction is not at all possible. And in the case of half duplex, the two-way transaction is possible, but simultaneously it is not possible. Suppose if one is acting as the transistor, two-way, right? So one is the transistor and the other one is the receiver. So the transmitter will transmit, the receiver will receive. Then after some time, suppose if you want to swap the charges, right? So the transmitter will become the receiver, the receiver will become the transmitter, so that the reverse transaction can happen, but not simultaneously. But if it is a full duplex, both the things will be having both transmitters and receivers, so simultaneous data transactions can happen. That is called full duplex. Again, you might have already studied this in your communication systems, a simplex, half duplex and the full duplex systems. It's a bidirectional. So the direction or in both the directions the data can flow. Fine. And the concept of I2C, right, was developed by Philips Semiconductor in early 1980s. And the original intention of I2C was to provide an easy way of connection between the microprocessor and the peripheral chips.